Hi guys, in this lecture we will talk about system type and steady state errors. A stable system can be classified with its system type. Now, if a system has a finite constant steady state error for certain reference input of certain degree, the order of that system will be equal to the order of that input. Suppose if we have a system and we don't know its order, if we apply a ramp input to it and it has a finite constant steady state error, we will say that that system is type 1. Similarly, if we apply parabola to it and its steady state error is non-zero finite constant, then we will say that its order is 2. Similarly, if we apply a hyperbola to a system and its steady state error results in a non-zero finite value, we will say that the system is of order 3. Before going to know what is that order, we must know what that steady state error is and how do we compute the steady state error. So let's define the steady state error. In order to know the steady state error, we have to consult the final value theorem.
Suppose for a certain function we want to find the final value, we want to apply the final value theorem. We want to know the value of a function at infinity. So let's write it. So this is the final value theorem. For a certain function, if we want to find the value of infinity, we use this formula, limit s tends to 0 s f of s.
Let's consider this unity feedback system with a controller T and plant G. Now we want to know the error for this. We want to compute the steady state error for this particular system. So how do we do it? We define this E to be the error signal, which is the difference between this reference input R and this closed loop output YCL. So I must write ECL, which is the steady state error for this closed loop system. So ECL is now equal to R minus YCL.
We know that YCL, if I write the transfer function YCL of S or R of S for this system is equal to, by the feedback, you know this is a feedback loop, so I must write D G 1 plus, remember that we have minus sign here, so I will have plus sign here, 1 plus D G. So from this transfer function I can write YCL is actually DG 1 plus DG into R. Okay,
now putting the value of YCL that we already derived here, we can write this DG1 over 1 plus DG into R. I will take this R common and say that this is D1 plus DG minus DG over 1 plus DG. Okay, this is resulting in this cancels out, so I can write 1 over 1 plus DG into R. So this is the result we are talking about. So I can replace this DG by L. I can name it L. L is loop gain, nothing else. It is loop gain. I can rewrite this ECL. Actually, this is ECL, by the way. I can rewrite this ECL by just replacing this formula. I can just simply write 1 over 1 plus L into R, which is actually easy for us to follow. Now, as we can see that I have replaced this loop gain by this L now, so I can write this E is equal to 1 over 1 plus L into R. Let's consider a unit step input. I know that we have E is equal to 1 over 1 plus L into R, and R is 1 over T for step input, and its Laplace transform is 1 over S. So I am now writing the steady state formula, which is limit s tends to 0, s 1 over 1 plus L of s into R of s. This is from here. Okay, we are just putting the limits s tends to 0. Now if I use this R of s instead of R of s, if I put this 1 over s, this s cancels with this s, so I am left with only this formula. So is equal to E of s. I can also say that this L of s is loop gain. I can also call it GOL, which means open loop gain of a system. So you may have different names for it. We will be seeing them later. Okay, now consider this open loop gain, GOL or L of s. It depends on you if you call it L or GOL of s. It's up to you, but we have this loop gain now, and I'm interested in knowing the order of this system. So if I apply unit step, I can write the unit step as 1 of t, or I can rewrite it like this: 1 of t, t power 0. This t power 0 is mean its degree is 0, degree is 0, as you see. Okay, now the s domain for this step is 1 over s. I am just using that formula that we have seen it previously in our slides. 1 over 1 plus L into R. Now instead of R I am putting 1 over s, and instead of L I am putting this thing here. So what happens is I am now using the formula ESS, element s tends to 0, s into this thing. So if I simplify, I am getting this thing which is resulting in B over A plus B. Now since A and B both are constants, finite constants, so this means that the error that I am getting here is a finite non-zero finite value. So for type 0 input, the steady state error is non-zero and finite. So this means that this is type 0 system. This system is type 0, since for type 0 input it is giving us a steady state error of finite non-zero finite value. So this is type 0 system. Okay, what will happen if I apply ramp input to the same system, the same earlier system where I had applied step input? Now I want to apply a ramp input to it. Let's see. Ramp input can be represented by 1 of t. Now notice this, the order of this polynomial t power 1. It is now 1. Okay, if I take the Laplace, it is 1 over s square. The rest is exactly the same. Just put the values of r, which is 1 over s square, and L is the same as it was in previous case. So I am now using the formula, this ESS steady state error, limit s tends to 0. Just simplifying things so that I can say, okay, this is cancelled with s, so I'm left with 1s only. Now I'm putting s equal to 0, so this thing ultimately gives me infinity. Now see that the input is a ramp of order 1, and it is giving me an infinite value. So a type 0 system has infinite steady state error with a first order time input signal. This is the conclusion. If we apply an input of higher order than the order of the system, the steady state error will always be infinite. Keep this in mind. In order to make this thing very much clear, I am now applying a parabolic input to the same system which we had already determined to be a type 0 system. Since this is a type 0 system, and we want to know what will happen if we apply our parabolic input to it. Parabolic input is of order 2. Since this is higher than the order of the system, we must expect that the steady state error must be infinity. And once I do that and I go to the same computations, I can easily see that the steady state error is infinity. So it should be very clear in your mind that if you apply an input to a system whose order is less than the order of the input signal, the steady state error will be infinity. Okay, for this example I have changed the open loop transfer function a little bit. We have modified it a little bit from the previous case, and now I'm repeating the same procedure. We will first apply the step input, which is of degree 0, and going through the procedure as we gone through previously, and we will find out the steady state error. Now I can see that the steady state error here is 0. We cannot tell the type of the system with 0 state. We must get a steady state error which is non-zero and infinite. We are applying a ramp input here of order 1. Transform for this ramp input is 1 over s square. And now I am putting this transfer function, the ramp, and all together, and I am finding out the steady state error. And I can see that the steady state error is finite, a non-zero finite value. So this means that this system is type 1. This system is type 1. We know that a system type will be 1 if it is giving us a non-zero finite steady state error for an input of type 1. Since this is happening here, so that's why we are saying this is type 1. Let's check the same system, type 1 system. Now we know that this is type 1 system, right? We already determined this is type 1. Now we are checking this for a parabola input. We are applying a parabola of d square, and we want to see what should we expect. Since this is of higher order, this input is of higher order than the type of the system, we must expect the steady state error will be infinity, and after computation we can see that it is infinity. So conclusion from this will be a type 1 system has an infinite steady state error with a second order time input signal. This is what we must take out from the slide. Okay, now I have changed this transfer function a little bit. Now we have put s square here instead of s. You can note that, and I will check for unit step again. We want to know the order of this system, so we are applying our step input, which is 1 over s in s domain, and going through the same procedure. I saw that the steady state error is now 0. This is not clear since we don't know the order of the system yet, because we must get a steady state error of finite value, a non-zero finite value. If we for a certain input, if we get a non-zero finite value for steady state error, we will immediately come and check the order of that input. We will immediately realize the order of the system. So let's see. Now I'm applying parabola input to the same system, and I am seeing that we are getting a steady state error, a non-zero finite value. This system is a type 2 system because of non-zero finite steady state error for a parabolic input of order 2. Similarly, you can find the type 3 systems and type 4 systems and so on.
This is it for today's lecture, and next lecture we will be talking about zero error constants. Thank you. Thanks for watching.